Okay, everybody, hello, welcome back. Final talk of the morning. Our speaker is Wei Jiang, and he will be telling us about towards the Craw Reid recipe in dimension 4.
Yeah, thank you very much. Hello, my name is Wei Jiang, and I'm from Warwick. I'm a master's student, just graduated this year. So this talk was based on a master's thesis I did with Craw Reid, based on a lot of things he did in past 20 years, I guess. Yeah, so let's start. In 1934, Miles made a conjecture between the Kribben resolution of a quotient variety. So I wrote a quotient variety of this type. So be secant over some G, where this G is a finite abelian finite subgroup of SL and CN. Yeah, so assume we have a Kribben resolution, and Chandler says we wish to find these bijections between. So we see we have a group and we have a variety Y. So we wish to find this kind of projections between like irreducible G and the base, that's too small, sorry. This of the cohomology of that cohomology of Y. Yeah. So to make it more precise, he made another conjecture in 1997. So, which says like there's two parts. First part is okay. I never spelled that right, but we can forget later, so don't worry. But dear, Y locally free and form a Z basis. Basis of the theory. So this part was already proved if for G being a finite abelian subgroup. So so we can forget all of these because if this so from now on we don't need to worry about the term G. If we can just treat them as vector bundles. Yeah, just all the use of it. So and the second part is the thing we're trying to do is we're trying to find a cookery with Chern classes of FIs, which will leads us to a Z basis of basis. Sorry. Z. Yeah. The basis of which the above thing hold. So yeah, that's the boring part. So let's start with us. From now on, I will try to explain this recipe and stuff we do from the simplest example of dimension 2, which is well established from dimension. So I will try to it's from dimension 2 to 3. The dimension 3 is where they actually did the Craw Reid recipe on and try to extend it to dimension 4. So, oh, should I just touch it? And
Yeah, so we touch the move it. Yeah.
Okay, that's the other side. Okay. Let's maybe start with the dimension 2 case. So
why is a crescent resolution?
Or why is it crescent resolution?
Assumed to exist. Do we know what? Sorry.
Oh, what would
naive question? Okay, but do we know when they exist? The crescent resolutions. Okay. But we do know the classification of those groups. But here, I guess what this.
Oh, actually, I will.
Something about G as well.
Yes. But as we say, like the G is the subgroup of finite abelian subgroup of SL and C.
Yeah, but there are many such things. I mean, you're not gonna.
I think it was proved that all of these have a equivalent resolution. But okay, for dimension 2 and 3, that's okay. Yeah. But for dimension 4, I will explain like when I will tell you the criteria later. Like there's a criteria for where for the case where they actually have a equivalent resolution. I'll explain later. So. Oh yeah. So for dimension 2, we do. So think of a subgroup of SL2. So we can think of it as we can start with a cyclic group. So maybe something like 1 of R A of the form 1 of R B. So write this as what I mean by this is I just apply this to the coordinates of x, y, and mod R. So which means like if x, y, I send to apply ax, by. Oh no, really, sorry, not this. Yeah. So I just use this to send as a cyclic group to act on C2. On C2, okay. 2. So what we actually consider, we're considering that we use this point to generate a lattice on C2. So on L2, so it would be something like yeah. No, let's do that drawing. I'm sorry. Yeah, so we can consider a Newton a Newton hole, which would start from point 0, 1, 0. Yeah. Do this. So for all the points, well, that's not really convex. We pretend it's convex. Sorry. Yeah. So for all the points there, so we have a few properties. Is firstly, any two consecutive. Oh, we could maybe call them from E0 to EK. Yeah. Yes. For all these points, for any two consecutive points, they form an oriented basis of this lattice. And for every three consecutive points, they have a relation, something like EI plus 1 plus EI minus 1 equals to some AI EI. Yeah, but I forgot to mention. So actually, we're not doing strictly to this thing. We're actually, we do some transformation to make it into the form of something like a 1C or form of this. And then we use this to generate this lattice. Oh, the R is not really in the, oh yes. Oh, the R is the kind of order of the group. Yeah. Yeah. But, sorry, can you say where you generate the lattice? Yeah. Oh yeah, because lattices are formed by these points, 1 over 1C. So you can see like as maybe that's maybe 1C, and that's 1 over 2C. Yeah. Sorry. Yeah, that 2 plus that times R of R 1C. Yeah. That. See that clearly? Sorry. Okay. The interesting part is actually, yes, these AIs. These, if we write them in this in a continued fraction, A1 to maybe AK, all these, if you treat it as a continued fraction, it's actually equals to R over C. But okay, from I mean, I asked a few of my computer science friends, but they definitely have a different opinion on continuous fraction. I don't know what continuous fraction means to you, but to me, it means, it just says that equals to 1 plus 1 over 1. Oh, sorry, A1 plus 1 over A2 plus. So it's a plus. Some of them put minus sign here for some reason. I don't know. Okay. And yes. Yes, that's how we do this. I want time for that. Okay. So we have this method, and we can move to a dimension 3 case. So if you think of a dimension 3 case, also we will treat we'll have some group of the form. So with some simplification, 1 maybe A, B. So right, something like this, and we can use these to generate a lattice. And think about that. All these points, where it lies on, this lies on a triangle which formed by okay, that's three axes. The 3 axes, we may call them E1, E2, E3. So all these points, the point that we if you try to do the analog from the dimension 2 case, we only consider the point that lies on the triangle. 1, 2, 3. Yeah, which lies in the first quadrant, octant. Yeah. So it'd be maybe few like this one here. And yes. So what we do is we can kind of project it to project along one of the axes. If we project it along the one of the axis, and they actually will become like, if we could project it over the last one, they'll become, it'll look like something like 1A. So you can see this. We go back to the we go back to the dimension 2 case, and if we try to calculate the continued fraction, but actually not for the continued fraction for these. No, actually we need to do some more works, but I won't explain the detail here. Continued fraction, then we can do this process for each of this each one of this, and then we can a little bit more detail, I think. Yeah, we can generate like a continued fraction for each of, like based on each of the vertex. Now what we do is we can, okay, if you think of these two, if you think, so we have like three pairs of vectors. If you look at from each vertex, we can pick all three and pick them to the same point, and there will be something like this. No, not this. They look like. So yeah. Yeah, if we invert one of them, then they just become half space. I forgot what my notations. So for each of them, for each of these O's, we have a continued fraction. The thing is how we can kind of all them together. There's a theorem says like, so only ratio we need to consider about it. If you remember, these continued fraction ratio, the number just correspond to the relation between 3 consecutive vectors. So to concatenate all of them, the only thing we need to consider are like the ratio between these 3 and the ratio between these 3. Right. So there's a theorem like that it happens like it's only possible to for each of the three sides. It's only possible for one of them to have the number bigger than 1. What I mean by that is, if we call that vector, okay, if that's E1 and that's V and W, yeah. So we know W plus V equals to some a number of E2. It says like for each of the EIs, this A, at most one of them, these A's can be greater than 1. So the continued fraction I should. should have something like 1. Yeah, we can put them together as a continued fraction of this. And actually, by some calculation, we can actually remove these ones. We can remove these ones. So, because of this, since this one is a sum of so this one can be the middle vector can be think of as a sum of some ratio of sums of these two adjacent vectors. So I actually we can remove this one, and we just need to change a little bit of the ratio, because before the ratio of this one, so for the numbering this one is calculated by this one and this one. But since these three have relations, so this relation can be replaced by this vector, and this vector. But actually, the transformation wasn't that hard. The only thing we need to do is we just to replace with this -1, and j -1 and c1. To this step, but you can see we after the transformation, we just remove few of the vectors, and things come back again. So by the theorem, we did like let's say it's okay. There be only one like long side. With being long side means the ratio of this this number a is greater than 1. So we can say there's still at least two of them. These numbers being 1. So we can continue doing this. And at the end, you can see we'll reach 1, 1, 1. Yeah. And these correspond to a regular triple of the vectors. So by doing this process, making this process, we can find a regular tessellation of this big triangle into like small regular triangles. And the thing that's important is if we like this, we call that to denote the toric fan determined by the regular tessellation. Of the regular triangle. Then the toric variety that's like the real lattice is called the is the Nakamura's A U, but so it's denoted as maybe I'll put that. We know that as this. And this, okay, we call us group, wow. If we call us group A, okay, let's call us group A. And these two quotient variety is a equivalent resolution. Maybe I'll give you an example, like one real example. The example is formed, that rectangle was formed by, there is a group, the group we use. Yeah. The group like formed by this, generated by this. Sorry, example. So I'll use this example because this is easy to draw. And example is sorry. Okay. Is this picture clear enough? Okay, nice. Yeah, they can see like things like every single line here in this picture corresponds to exceptional curve P1. It's exceptional P1. So we need to find a way to parameterize this. The way we do it is we find a coordinate on them. So for each of these lattice points, so you can see each line has two like adjacent, already is linking like two of these points. So what we do is we write these two coordinates together, like for this one, for the first two is 1. Okay, we ignore the 1 over 11 for now. This point is 1 to 8. The next point is, and this point is 2, 4, 5, 16. And we just put them together and find the minors. And the minor will be some number, like 3 numbers. And we use this, each number just represents the power of our, like the first one corresponds to the power of x. The second one corresponds to the power of, if it's I, j, k, then the coordinate we use will be I, xi, y to the power of j, and z to the power of k. And as here, since our group is of the form this, we say like our X has character 1 and the Y has character 2 and then has character 8. So we can we can use these we can give this polynomial like usually because there should be like usually there will be a one of these or two of them will be negative. So it's actually not just polynomials, it's actually a ratio of polynomials. So for example, it will be something like x2. Do I have example here? No, I didn't put one. Maybe like x2 y3 over x2z over y5, y5, yeah. And for this one, we just pick like either the bottom or the top and the bottom, and you can see x, if x has character 1, then has character 8, then the top thing have character 10, and the bottom thing have character 10. Yeah, usually this character match up. So we can use these to label each of the lines by number. So in this case, I guess we will label them by 2. 8, 6, 5, and 8. As you can immediately observe that at each of the point, something quite interesting. Like for example, this point, there are 3 lines. Well, 2 pairs of lines marked with 1, and one pair of line marked with 1, and one pair marked with 2, and a single one marked with 6. So we can mark this one by the sum of 1 plus 2, which is 3. And for I think like here, you can see this point. They have 4 lines coming, and a pair marked with 2 and a pair marked with 8. Yeah, we can mark with 10. And why are we doing this? The reason why we do this is we can try to uncover some relation between the bundle of the forms in this form and the character of the group. So these numbers are character of group. So if we have like a bundle f of m, which we correspond to this point, which equals to k tensoring f of l. And that corresponds to a character like chi of m equals to chi of k plus chi of m. And this works out quite well in dimension 3. Okay. I'll quickly go through the dimension 4 case.
So, I mean, just what is this? I mean, are we? I'm sorry. Just so a representation is what? Is it? Huh? No, but does this have to do with?
A frequent resolution is a subdivision of the first quadrant using only Julian lattice points.
I'm okay with
That's
this.
what this picture is.
But is this like so the fact that this being G Hill, but in this context, a bit of a red herring. I have the quotient singularity, and it has a derived category where the line bundle is given precisely by representation. In fact, all these were the reps here are one dimension. So
These
the
are-
red calculus generated by those line bundles. And are you saying that that line bundle is sent under the BKR correspondence to the structure sheaf of the corresponding
This
decorated?
was before that. This is the line bundle, for example, the line bundle that he wrote down there that has sections extra 2 cents or something I can't read, divided by y to the fifth, right? That
Yeah.
corresponds to character N.
Yeah.
That marks one of those lines. It's a line bundle, and you're using the first term class of that line bundle as the dual class to the class of that line.
Right,
When
but
you
so
consider
now, but
some-
why do you say that the line bundle corresponds to a monomial? What does that do? I mean, we are.
That kind of the coordinate parameterize it,
The what?
the coordinate, the parameterization of
The
that.
group is acting in the XYZ. The character spaces correspond to ratios between two monomials in the same character space, correspond to sections of the Gonzalez spring Valverde line bundles. Yes, and these are tautological line bundles arising from the A hill.
I see, but so in other words, we are completely and totally always on one side of the drug category, namely, we're translating from looking at it as a hill and therefore the G-equivariant sheets of zero-dimensional sheets of C3.
If you believe
And on the other hand, this particular, the resolution seen as from the toric picture. And then you're telling me what the term character of your class of that, the first term class of line.
Look, he said cookery. The point is,
It's cooking, but it cooks something. I don't know what something does it cook.
the line bundles give you a basis for the cases.
Yeah, I get that.
The churn classes of the base of the churn classes give you certain classes out of which you can cobble together a basis for the curve.
Yes, and
So you have to sort of take some combinations of them to mark the.
but so look, I mean, I see, for example, I see I see many twos in there. What does that mean?
Oh,
In fact,
this-
there is a whole inner curve of twos.
Yeah.
What exactly does that mean? What is that two?
The-
There is a particular
That
character.
means you take the sheaf on X corresponding to
Yeah.
character space 2 on all the functions that live in the character space 2, and you blow that up, right? And that will be the ample divisor on, if you take that picture, you pull it up out of the single vertex for all those things minutes, using the channel,
Yes.
then that will be, that's the blow up of that idea.
Yeah.
Yes. Look, it hasn't
Oh.
yet had a chance to say anything from that before that.
But yeah, but I mean, that's okay. I understand this. And I just wonder what are people doing behind it, because I mean, that's fine. But they will take another hour to begin to talk about the four-dimensional case, but we haven't even understood what this stuff means in the three-dimensional case. What point is there in us listening to the four-dimensional case? So, I mean,
Sorry, I
it
didn't
would be
explain
nice
that
to know
well.
what this stuff means, So there are three things in the picture. There is X, there is the A cube, and there is, no, because A cube is something, but we don't, it's probably, you're saying isomorphic to this Y.
If it wasn't a hill, then the Springway Verde sheaves would not be line bundles. We want them to be vector line bound, so we take their term classes without having to worry too much about that. Yes, these are having got the area as it happens to be a proper solution in this case. If we are to try and transform a basis of the K theory into the basis of the harmonics.
Let's go back to basics. Okay, so now you're two, for me, two there is a character or
Yes.
mu element.
Yes,
So then out of that, I make a line bundle on X.
on a, you make a sheet, a divisorial sheet.
Yeah,
on
well,
X,
a Q line bundle on the stack, but yes. Now,
where it's a sheaf. It's a portion.
yeah, that's okay. That's
The thing that is an idea is to blow up that idea.
right.
Corresponds in toric geometry to taking that picture and lifting it up at the single point 2, making a piecewise linear function, which
Okay.
is which bends along those 2 lines.
Okay.
Yes, that's a separate resolution that pulls out only
Partial. Partial. It's, I got it. I got it.
Yeah.
Oh, okay. Oh, okay. So that's meaningful.
So look, we really, you know.
I guess we don't have time for that.
Try and finish.
I will try very quickly.
Try to say something amusing.
Okay,
Inside.
I'll try. Oops, sorry.
I'm sorry for heckling you.
It's okay. I'm sorry. I don't think I explained that really well.
I don't know why you're having meetings. It's better if one people different from your supervisor understand.
Yeah, I know. I know. Okay, let's quickly go to the dimension 4 case. So for dimension 4 case, firstly, we only consider a simpler case which does not differ from the dimension 3 case. We only consider saying groups of the form 1, 1, A, B. Yeah, and you can see if you draw a picture of the junior singular, how does it?
Sorry, you write 1 over R 1, 1, A, B,
Yeah.
but
Oh, the R equals to 1 plus 3. Sorry.
I tend to write 1 A minus A B minus B, but then prefer this way.
Yeah, because I have to do
This
the.
is not, sorry. This is a
This is something
SL. Okay,
Yeah.
okay, thank you.
Okay, it's all the group I mentioned is in the subgroup finite
And you
number of
wanted
group.
to have a correct resolution, so I said.
Yeah, that
example,
criteria is
1
coming.
over R, A minus A, B minus B. But that's terminal, and will not have anything like this going on, right?
I'll tell you.
Yeah.
I'll tell you next, like about the criteria. So we only consider all the points if you think of like E1, E2, E3, maybe E4, E1, E2, E3, E4, and you can see we have a tetrahedron. I didn't draw that well, but you can see the tetrahedron structure from this. I guess you're expert in geometry, you know.
Yeah.
And
It's not a great paper, but
okay, so all the points here you can see is the first 2 columns the same. So they all and they plot together to R. So they all lies on this triangle. So if you take the midpoint of E1, E2, we call that A, and this triangle, it all lies on this triangle. So this A, E3, E4. Yeah, and there's some problem with this A because the coordinate of A, if you see that's half of E1 plus E2, right? So
Yeah.
there's a problem like if so there's something to do with R. So if R is not an even number, if R is an even number, then it's okay because A is a lattice point. But if R is not even number, then this won't be even like a lattice point. So there's some problem with like what we do with this A. But if it is a lattice point, there's no difference between this and the dimension 3 case. So we only consider the case when it's not at this point. But so similarly, we can do a kind of a tessellation, but I can tell the tessellation a little different than the dimension 3 case. I will just maybe do a simple example. Maybe I'll do the same example. Okay. Yeah, maybe I'll do this. Yeah, all the triangles other than has no link to this point. Okay, it's not really a lattice point here, so I draw this. This you can see. So there's E1 above and the E2 like below. So they are the two tetrahedrons, right? But except for these points, we have a link with like these triangles have a vertex of A. So if A is not a lattice point, we have to consider both of the E1 and E2 to form a simplex.
The triangle is called the
Median junior triangle, yeah.
And the point A is not.
And
So we're playing the same.
okay, and I will give you a quick thing. So if we let H to be the highest common factor of R and A, and okay, if H equals 1, then we can see there's a unique way of writing H by some A times C plus R times X, where C and X are unique. If it's not unique, if H is greater than 1, then there may be possible a lot of value of C. So what we chose, we chose C to be R minus, okay, sorry. We chose C such that this number, which R minus 2C minus H modular R is smallest. We chose C to make this number smallest. And we consider the point, this point, 1 of R, C, C, H, W. And we'll consider this continued fraction, H times W, maybe equals to B1, B2. According to a PhD thesis by Sarah Davis, which is who is a former PhD student of Miles. Sarah Davis, is that correct? Okay. According to her, the criteria for the existence of a Kribben resolution is PC is a junior point. By junior point, we mean like the sum of them equals to R. Actually, not one of like all the sum of these equals to R, other than multiple R, and all of the BI's is even. Yeah, that's a if only if statement. So if this is true, then it's Kribben resolution. If it's not true, no Kribben resolution. Okay. Now we need to go to the. I'll give you a quick thing about why dimension 4 is interesting. I'll do that with an example. So things won't happen in dimension 3. It happens in dimension 4. So the example I will use is, of course. Is this group 1 over maybe it's more okay. 1 over 23, 1, 1, 3, 18. Especially thing, I'll draw the diagram quickly. Yeah. Yeah. The thing will happen in dimension 4 that won't happen in dimension 3 is we get this kind of a parallelogram inside of the when we try to do the tessellation. So there's two ways of triangulating. We can either do this way or we can do this way. And if we try to mark them by the character, this one I think is marked by 8, and this one marked by 15. Oh, so the marking will be similar, just similar as the dimension, actually exactly the same as the dimension 3 case, the marking. And the thing is, if we consider one of the triangles and try to generate like a basis for the hill for the module. For any other triangle except from these traps, the number of the bases is exactly 23. So match up with and actually the bases like you see this group have over 23. So you have character like from 1 to 23, and these bases each one lives in one of so there's a one-to-one correspondence between the character and these bases polynomials. But for triangles here, inside here, one of them has 24 polynomials, very close. So there's the thing is, they are, so by pigeonhole theorem, there's actually at least like 2 polynomials in the same character space. Astonishingly, like the character space which have problems exactly 8 is 8 or 15. So in this case 8, we have 2. Oh, it's not 15, sorry, 15. I have 2 polynomials, that 5 and x squared times t squared. Both lives in the 15 characters, the character space 15. So what we're trying to do now, so this is a working project, so it's not finished yet. So what we're trying to do now is we're trying to, so usually like for this case, we can use 1 to generate all the other things, all the other polynomials. But for this case, what we're trying to do is we're trying to use not just 1 character generator, but use 2, but the other 2 has a property like, so these 2 are related by a relation equation of this, b times x squared times t. Oh, maybe I should mention what the ABCD is. C times, sorry, I was copying that from the computing code. So there's a star for the multiplication. Yeah, F5. Yeah. And
what is that polynomial?
Yes, that's what I want to say. Like I forgot to explain now.
What does it mean?
When you make that triangulation,
Yeah.
for each triangle, you can write down a dual basis of lower polynomials. Yes, and you can use these, you can write them as ratios of 2 positive polynomials and use those to define a cluster. Yes?
Yeah.
Now, if it's the A hill is exactly the diagram, and that is not equivalent resolution.
Right.
So we have to choose one of those 2 floppy.
The difference, the 8 hill is this thing where the square has not been subdivided.
Where the A-hill has
been
been
subdivided.
into 4.
Yeah,
Yeah, so we only chose one of them.
Not preference.
right, right.
Yeah,
Actually, we chose this one.
and so the ABC are whatever ratios, the dual basis to the side. Yeah. So I'm hoping to get a cluster, and instead of getting 23 monopoles, I'm getting 24 monopoles with that BC relation between the two, you know, the two bad monopoles.
To these two. Yeah, and yeah, I think that's nearly all of my talk.
Yeah.
Really sorry, I didn't present that really well, and I don't have time for the dimension 4 case. And thank you very much.
Yes.
Any more questions?
Sorry for all the interruption.
Let's,
Well, I'm apologizing for me. I mean,
let's thank Wei again.
that's my
So
job.
the next talk will be an hour and a half from now, 2 o'clock.
Oh, what should I do with this? I just.
Oh, plug it back into the door.
Oh, I see.
That way, yep, that's the one. And that will charge it back up.